So it's time. Let's start. Oh, you can start.
Great, thanks. Right, so let's start by picking up where we were yesterday and did a quick summary of what we have observed yesterday. So there, we've introduced the Poch's rotation very quickly, just by picture. Is that if we have a longest path P, we fix one endpoint, okay? And then we look at the other endpoints. If there is an edge, if it has a neighbor, then we can rotate like this. So then, as a consequence, we get a new starting point. Okay, this is basically Poch's rotation in one picture. Now, the take home, there lots of definitions and things, but really the take home yesterday is this lemma 4.2, Poch's lemma. Which says that if we have a vertex, a path P, longest path, from U to V, say, and in the graph G, longest, then if you write S to be all possible set of starting points we can obtain from rotating P fixing V, then what we have is that the neighborhood, well, actually what we have more detailed picture. The neighborhood of S has to be in S plus minus, its original neighbor on the path P. Okay, but oftentimes what we're using is using its consequence. So this implies that N of S does not expand. Okay, this is really the take home. So let me do a remark here, which I haven't managed to, well, I kind of explain it through this example. So here a remark is that how it's used, right? How Poch's lemma useful. Well, I'll just briefly write it. Basically, it implies that this lemma implies that S does not expand. Well, the set of all possible starting points obtained from rotation. Okay? Then, okay, how does this help us? Now, if we know this, if we given this fact plus that we given the graph G has expansion for small sets, for example, we have this 2K expander saying that you have 2 expansion for all sets up to size K. Then we know that since S does not expand, but G has expansion for small sets, this must imply that S is not small, it must be large. Okay? In this 2K expansion notation, that means S is at least K. Okay? In a nutshell. And then how this was used is, now this is the consequence. If we have this additional expansion, if we have this additional expansion property, we imply that S is large. Now, how this is used is that if now we have large set expansion, which was exercise, which, okay, let me just directly write here, saying that if you have some set of size n over c, remember, some 10 maybe, set U, then its neighborhood is large, very large. Okay, so you have expansion, a very nice expansion for large sets. So plus this, basically, we get that we must have a long path in the graph. Okay, this is lemma 4.7. Basically, the proof by saying, okay, since we have this, well, first of all, large set expansion, we can bootstrap it to all small set expansion by removing a very small set of size 10n over c, such that the remaining graph is 2n over 5 expander. Okay, now we take the longest path in the remaining graph, g minus w, and let the vertices not in P to be z. So then we know S cannot send edges to z. Okay, but we also know that S is large, and we have large set expansion, so z cannot be of size 10n over c or above. Otherwise, the neighborhood of z would have intersect S, meaning that we have an edge here. So that's how we use it to find a long path in lemma 4.7. So this is the first take home, is that we really just need to remember it's often used combined with some expansion property with small sets. So all we really need to remember is that with the expansion, rotating after rotation, the set of starting points, there are many, many of them. Today, we will see the second consequence of Poch's lemma, how it can be used together with the extension edge sprinkling technique. So that's the second way of using it. Okay. Oh, by the way, yesterday, just one more thing is that in this lemma 4.4, we know that if you have a P, longest path, you rotate, you get an endpoint set. Then there exists a cycle whose vertex set contains S and its neighborhood. So this is also useful in finding long cycles. So this lemma is also, for example, it's used a couple of years ago for the Ramsey goodness of path. So today, what we want to talk about extension and edge sprinkling. Okay, I will explain each one of these terms. Combined with Poch's rotation, they give very nice results. So the main result in this subsection here is this lemma that we will see a proof of, lemma 4.12. It says the following. Let me just state the lemma directly. We have our graph. We have our graph G, which is drawn according to the random graph with some constant over n probability. Okay, we have a random graph with linearly number of edges. And then we have another graph, H0, our favorite 2n over 5 expander, meaning that we have 2 expansion for all sets up to size n over 5 on the same vertex set as G. Okay, so they have the same vertex sets. So now we want to put these two together. We want to combine their edge sets. The conclusion is that if you add on top of a 2n over 5 expander, a random graph Gn 500 over n, we will get a Hamiltonian graph. Okay, this is the main results that we would like to cover today. But it seems a little bit strange why we have this combination of expander and random graph. Let me just say very quickly a few sentences to anticipate its power. So basically, it's not so hard as we will see tomorrow to find a very, very large, almost spanning expander in the random graph when the probability is large enough. Then we will have our H0. Then we can do this sprinkling. We can add a little bit more edges on top of this expander, which is our G. So this is the edge sprinkling that I will surely explain later. So as a result, that implies that already immediately that the random graph has at least restricted to the large expander that we found is Hamiltonian. So this amounts to the problem of finding long cycle to the problem of finding a very large, almost spanning expander in random graph, for example. Then furthermore, if you want to prove that if you want to give a very sharp threshold of the appearance of Hamilton cycle in random graph, then that amounts to of proving that we can find a spanning 2n/5 expander in random graph with certain probability. If you can find a spanning one, then on top of that, you sprinkle some more edges, we make it Hamiltonian. So that's how we can see lemma 4.12 is applied. So it's very nice lemma. Okay. Now, before we explain the extension and edge sprinkling, these two terms, and give a formal proof of 4.12, let me just summarize this proof already with one sentence. So the take home today is this one sentence, but all the remaining is just details. So its proof, lemma 4.12, in a nutshell is that rotation yields Manning extension. Okay, then we can sprinkle edges in rounds, in multi-rounds, to elongate it, to make it longer. This is basically the proof in one sentence. Okay, two half sentence. Oh, why I keep doing this? I want this one. Okay. Good. So let's make this sentence rigorous. First, then I have to talk about extension. So for the extension, I'll give you some heuristics. So the heuristic is the following. What we're going to do is that we always start with Poiseuille's rotation applied on the longest path, P. So let's say we use Poiseuille rotation on the longest path P, fixing one endpoint V that we have before in the 2n/5 expander. Okay, suppose we do this. Remember that the remark I just make, the take-home remark we just make is that if you use lemma 4.2, the Poiseuille's rotation lemma, then we know that S does not expand. So if our graph is a 2n/5 expander, we get lots of starting point S. So what we have is that we get at least n/5 possible starting points. Okay, so let me draw a picture. So you can rotate many different ways n/5 such choices. Now for such a choice, let me fix such a choice. Use the red dot, right? For any such choice, for each, we can now fix our new guy. Fix any one of these. Oh, Jay-Hong, there's new people joining. If you can help me. So the right. So far we've only do one side post rotation. We fix always one end. So this is the black vertex on the right on the first picture. Then we get n over 5 all possible choices of starting point. Now for each one of these red starting points, we're gonna fix now the left end, and we do the rotation from this side. Okay. Then that means for each nonsense. So for each one of these new guy, we again get n over 5 choices, isn't it? Right? So it could be that this n over 5 red set and n over 5 blue set overlap, but at least we get quadratic many possible pairs of n points from different ends. Okay, so this in particular implies that when we do rotation on both ends, then this implies that rotating both ends, we get n squared, we get at least n over 5 choose 2 pairs. And what's important of this pair is that if you can ever add an edge between the red and the blue vertex, a red and its own blue set of vertices, there's a subtlety here. If you can add such a pair, then you close it up to a cycle, right? Let me draw the picture here. So if we can add such an edge, oh, this is too bright, I remember. Let me use purple. So if you can add such an edge, we close it to a cycle. So this is the extension by what we mean. Adding such pair, close path into a cycle. Now what's good about that? Imagine our graph is connected. Now we have our longest path being closed into a cycle. Since the graph is connected, if you ever have a vertex outside, you must send some edges somewhere to the cycle C. Then that means we can now elong our original path like this, by adding this vertex out of the cycle C. So this is the whole extension process. We want to always close it up into a cycle and use the connectivity of the graph G. Okay, so this is the extension. Now let's make it precise. By this. So this motivates the following notation. Let me let L of G to be the length of longest path. In G. Okay, then we say that a pair UV, a pair is a booster. We're boosting the cycle, right? It's a booster for G. If adding this edge make the longest path longer in our graph. Or if you cannot make it longer, then it makes it Hamiltonian. So it could be that we don't have this vertex outside anymore. That means C is already Hamiltonian, and we are happy. That's the longest possible path you can find. Okay, so this is notation. And a very quick observation follows. And it's a trivial observation, but very, very nice observation. worth written down separately is that now to prove a graph is Hamiltonian, then it suffices to show that it can be obtained from some some graph, a subgraph of itself, and then by adding up to n booster. Because every time when you add booster, you enlarge the path by 1 until you reach Hamiltonian state. So if you can add n boosters iteratively, then you boost the length by at least n, which means you must be Hamiltonian already. Okay? So to prove a graph is Hamiltonian, oh, sorry, it suffices, I'm not sure if I can. Suffices to show that this graph can be obtained from some graph G by adding its order number of boosters. Okay, so G is not our original graph. So you want to prove that our original graph is Hamiltonian, it's enough to say that there is some G, a spanning graph, then our graph is obtained by adding G boosters on it. So now, basically, how do we boost the length of the longest path? The task now is to be able to add this booster. This is where we're going to introduce the edge sprinkling, the second topic of today. Okay, this is the extension so far in the notation of booster. But let's summarize the extension, put the above observation into a lemma for 11. So the lemma says that if we have a 2n/5 expander, okay, then there are at least this many boosters. Okay, we've just said you rotate one, you fix one n, you rotate one side, you get n/5. You rotate, fix any one of these, you rotate the other side, you get n/5. So you get this many pairs of boosters. So, sorry, let me just silence it. Now, right, this is for the extension, the edge sprinkling. Okay, before the edge sprinkling, maybe it's good to get some preliminary written down. I think these are all basics, but it's good to be on the same page. Let's recall some basic. Before we get to the edge sprinkling. The first thing is we can expose edges. We can review or expose edges in the random graph in multi-rounds. This is allowed by this very simple proposition for 2.4. It says that if we have a random graph distributed as GNP1 and G2 distributed as GNP2, then if you take the union of them, it's distributed as GN P1 plus P2 minus P1 times P2. So just use inclusion, exclusion. It's very simple to prove this. So in particular, what it means is that if we have, I choose eraser again. If we have GN P1 plus P2, then we can imagine our random graph as the union of G1 and G2, right? That's all it means. Actually, with some surplus, we even have minus here, but we're not going to use that. So how we actually going to use it? So we can imagine our random graph is union of independent. Here, what's important is that these two are independent, G1 and G2, okay? Independent two random graph on the same set of vertices. Then we put them together. Okay. And the second thing is like concentration inequality. It gives also exponential decay like Chernoff. Same, but different, but almost the same. So it's about the, let's recall martingale. A martingale basically, it's a stochastic process that, let me write it down first. Or you can imagine it as a sequence of random variable, okay? Sequence of random variable, let's say we start with x0, x1, x2, ... With the following interesting property that what's happened long before has nothing to do with what's going to happen next. Okay. So the expectation of the current of, first of all, we need that this is integrable, so they all have finite expectation. And the important property is that the expectation of the next state, what's going to happen, given all previous states, equals to just one state, one timeline before. It has nothing to do with xi minus 1 or anything before that. So in the parentheses, in particular, we will use actually sub-martingale. Okay, we will use this guy, which correspond to this. That it's at least xi instead of equal to xi. Okay, so the expectation of the next state is at least as big as the previous state xi. Maybe this definition looks a little bit strange if you first seen it, and I'll give you a very intuitive example. A very intuitive example is gambler's fortune. Gambler's fortune. Okay, it's a typical example of martingale. I think it might be even the origin of martingale, actually. So imagine a gambler is gambling, of course, betting on, say, let's look at the simplest model of the outcome of a coin flip, okay? Let's say we gamble on coin flips. And this is the setup. And we're gonna let, let's say you win or lose one. This is the symbol for the Chinese money. So one whatever. If it is tail or tail, okay. So if it's head, you win $1. If it's tail, you lose $1. And we're gonna let xi be his money, the total sum, his fortune after ith bet. Okay. Then let's check. Well, of course, everything is finite. So we have the expectation of xi is finite. And if you look at expectation of xi plus 1, the expectation of next outcome, given that currently I have xi amount of money, it's the same as xi because the next coin flip, it has 50-50 to be tail or head. So it doesn't add anything to it. This is a martingale. Okay. So what's nice is that when we have a martingale with bounded difference, we can give exponential decay. So this is the Azuma-Hofting inequality. It says that I will take an easier applied version. Let's start with a 0, okay? And then we have x1, this is sequence of random variable, to xm, be a sub-martingale. With bounded difference, that means every 2 consecutive states, they don't vary too much, kind of like a Lipschitz condition for each I during this process. Then, for any lambda bigger than 0, we have an exponential decay. Okay, so usually we imagine all CI to be the same. Then in the denominator, you basically have the length of the sequence m squared. Oh no, m say, if CI is a constant, view as constant. So you have the deviation square, lambda, over m. Okay, and if the deviation is proportional to the length of the sequence m, then you have e to the negative m. That's exponential decay in terms of the length of the sequence. Usually that's how we apply. Okay, let's get back to our business. Talk about sprinkling. Okay, we'll continue from the booster. So I think the Samsung Note app, it has like a tiny auto correction to make your handwriting slightly better. So yes, it looks ugly here, but it's already a better version of my handwriting. In other app, my handwriting is worse. Anyway, so the edge sprinkling, what does it mean? Let me first write it down. Basically, okay, maybe it's better if I illustrate it with a picture than I wrote a description down, informal description. So here maybe it's a picture to keep in mind. Remember that after the rotation on the expander, 2n/5 expander, say, then we get quadratic many possible extensions, meaning that any of this dotted edge, missing edge, if you add it, then we can elong the length of the longest path, right? So now what we're gonna do, so we have omega n squared many boosters. So what we're gonna do is we're gonna expose edges in multi-rounds using this proposition 2.4. We can imagine GNP to be GN, the union of GNPI, where the sum of PI is P, right? So we're going to expose edges in multi-round, and this is the name sprinkling. We kind of imagine that we're baking a cake, that's the base graph, and then we're going to sprinkle more and more edges in multi-rounds. Okay, so in particular, what we're going to do is we will make use of observation 4.10, saying that to make it Hamiltonian, we just need to add n boosters. Okay, so we will sprinkle in n rounds, maybe some large constant times n rounds, and each round it's enough to sprinkle constant many edges. Then we have a positive probability to add one booster. Then after some large constant times n, linearly number of rounds, we've added with high probability n boosters, making it Hamiltonian. That's the idea. Okay. So we've always working in the regime where P is some lower bounded by some constant times 1/n, large constants actually. So the idea is that rather than revealing all edges at once, we can sprinkle them in, this is important, linearly in n many rounds, and each round constantly many edges. Okay, now since we have quadratic number of booster, just do a very basic random intuition. If you have quadratic number of booster, and we only have n choose 2 number of edges, right? So if you randomly sprinkle a single edge, you have positive probability to hit this booster. So if you sprinkle a large constant number of edges, we can use this concentration inequality to prove that there's a high probability that we will hit one of this booster. So this is for this one round, okay? Then we sprinkle a large number times n rounds, we get what we want. So then that means each round we have positive probability to add a booster. This is why we choose n round. And it's okay because n rounds, each round, constant number of edges, we only add constant in linear in n many edges, which is gn c over n. Okay, so all this intuition here basically summarized formally to our lemma, main lemma, which I stated at the beginning of the section, this lemma. We start with our expander H0, and we get our graph. We're going to sprinkle on top of H0 this graph G, 500 n over n. We will view this G as linear in n number of random graphs, union of this many, independent of each other, each with constant number of edges. So let's see the formal proof. I think I've half of the time I'm saying that I leave it as exercise. So this time let's actually see some details. And the details is not that long either. So let's prove this 412. Let me quickly recall the statement here. We want G is Gn 500 over n. H0 is 2n over 5 expander. We want to show that almost surely G unions H0 is Hamiltonian. Okay. So this is what we're going to do. We will sprinkle m rounds, which is linear in n. This is the number of rounds. And each round with probability 100 over n squared probability each round. So Gn 100 over n squared has constant number of edges. Like expectation is 50 edges, right? Each round, something like that. So we're going to define Gi distributed as Gnp. This p is 100 over n squared for each round. This every Gi is the sprinkle of the ith round, and this is independent of each other. Okay. So proposition 2.4, which is the union of random graph, implies that it suffices to prove, I will define H. Let me define Hi to be H0 union less equal or less? Less equal. Okay, so Hi is what? We start with H0 at time 0. You sprinkle G1, you get H1. That's the graph obtained after the first round sprinkling. Hi is the graph after the ith round sprinkling. We need to prove that Hm is Hamiltonian with high probability. Then we are done. This is what we want to do. Okay. So Gi is the graph sprinkled at ith round. So then, by observation, for 10, we know that it suffices to show with high probability, with probability tending to 1, at least n booster added. Okay, if n booster is added, we boost the length by at least n. That means the graph is Hamiltonian. For this purpose, to keep track of how many boosters is added, we're going to define this our random variable, which will form a martingale. So we define for each I in M, a random variable, yi to be the event, the indicator random variable of the event that Gi, good event, contains a booster for Hi minus 1. Okay, Hi minus 1 is the graph obtained after I minus 1's round. Now the Gi is the ith round sprinkling. It contains one booster for the previous round outcome. So this is the good event, Yi. So with this notation, that means we need to show the sum of this random variable Yi is at least n. Then we are done, right? Well, first thing to notice is that at any stage, every round we get this graph Hi or Hi minus 1 because it contains our original graph H0. So it's always a 2n/5 expander. The expansion is monotone increasing property, so we don't ruin it. In particular, that means for each one of these Hi, we can apply Poiseuille's lemma to see that it has lots of boosters. So that means by our lemma 4.2, we get that Hi minus 1 has at least n squared over 50 boosters. One of these lemma that we stated today. Okay, then we can compute the expectation of the event happening that we contain a booster. This event, because it's an indicator variable, it just equal to the probability that it's 1. When it's 0, it's nothing. So this is 1 minus. So this might be the most difficult part. Probability that 1 equal to 1 minus that. Okay, the equals to. Now let's estimate the probability that Yi equal to 0. It's 0 if none of these edges that we sprinkled hit one of these booster, right? So we have n squared over 50 choices. None of them get hit, independent of each other. So this is like that. After some computation, I will not do. It's at least 1/2. So in expectation, Yi has value 1/2. The probability that we have a booster is 1/2. Now it just followed by martingale, I think. So we're gonna define our martingale. We start with x0 equal to 0 and let xi, let's centralize the random variable. Okay, yj minus 1/2. For each I in m, if you centralize it, it's easy to check. I will not check that x0, x1 is a sub-martingale as we defined. So then Azuma-Hofting inequality, lemma 2.8, implies that we get that the probability that xm is less than negative n, so lambda we're going to take as n, is at most exponential decay with respect to the length. Because our boundary difference ci is always 1 here. I forgot to say, right? xi minus 1. Because each round, their difference is yj, yi minus 1/2. It's at most 1. Boundary difference. So we get this. And remember, we choose m to be 5n, linear in n. So this goes to 0. Okay. So what it implies is that, okay, what's the implication? That means with high probability, xm is equal to the sum of yi minus 1/2. But let me move the 1/2 out, okay? Is bigger than negative n. So if this fails, we have, if this fails, we have at least very high probability is at least n. But then this is exactly what we want. We want the sum of, where is it? We want the sum of yi to be at least n. Here, the sum of yi is at least m over 2 minus n, but m is 5n, right? We are done. So this is, we have a little bit time left. Maybe I will give a preview of what's going to happen tomorrow. Right. So once again, let me give you the big picture, and it will motivate what's going to happen. Oh, maybe before that, yes, okay. So what we have seen, we've seen that lemma 412, it says that if we have g, that's gn, some constant over n, h0 is 2n over 5 expander, then we know that if you put them together, it's almost surely Hamiltonian. So in particular, this means that if we want long or Hamiltonian cycle in GMP, by just splitting some, by exposing a little bit more edges later on, we just need to prove that GMP contains a large expander, right? This, wanting a long cycle in GMP boils down the problem of finding a large 2n over 5 expander. So we want to find such a H0, which occupy as many vertices as possible in GMP. Then we sprinkle a little bit more, 500 over n, edges on top of that. Okay, so this is what will happen tomorrow, section 4.4 of finding large 2n over 5 expander in pseudo-random graph. We will define some some stuff.
So there is question on the chatting.
Right. Okay. The question is why we cannot use the linearity of expectation to say that the sum of yi is at least 5n over 2. It's not that we need the expectation of the sum to be big. We need the actual random variable sum of yi to be big, at least n. We need this one, right? Not its expectation is large. But since we know its expectation is large and the dependency is weak because it's martingale, so you can use concentration to show that its actual value, sum of yi, is not so far away from its expectation. In particular, it's at least n with a very high probability. Okay? You are right, we can do linearity of expectation, but I only give you the expectation is large, not the actual random variable is large. So, right, so on the big picture, this boils down to finding large expander. If we can find large expander combined with lemma 412, this very useful one, then we get Hamiltonicity or long cycle. This is what we will do tomorrow. So maybe we finish today by more questions. I will not say more new material. So let's see the question. So it is related with our construction of HM step by step, right? Yeah, because it's step by step, and every step it increased by most one. So it's this is where the Lipschitz condition comes in, boundary difference. Is that what you're asking? I will share my notes because I'm still proofreading the notes, maybe at the end of the course next week at some point. So you will get you will gradually, so maybe some of you are experts, so these are rather basic, but you will gradually get, I will put some newer and newer results. Eventually we will see the probability threshold for the appearance of spanning boundary degree tree in the random graph, which was a very nice advancement a couple of years ago, reducing to log n over n, but we will show polylog over n, a slightly weaker result. It already contains lots of new ideas. So let me zoom into today's most important lemma, and we wait for a couple more questions if you have. So now if you read this sentence covered by this yellow color, it kind of makes sense now, right? So we have our random graph G and the H0 expander. It's almost surely Hamiltonian because refers to rotation, there are many possible extensions. They're going to sprinkle edges in rounds and to boost it, eventually become Hamiltonian.
So anyone has any other questions?
Or to motivate you a little bit more, using this lemma, later on we will see a slightly more modern proof of the sharp threshold of Hamiltonian cycle appearance. So we will see that it's log n plus log n plus some little omega 1 over n, a very sharp threshold. We will not prove the hitting time result, but this we will prove that one.
Okay, if no question, let's end the lecture here. Yeah, thank you for the good lecture.
Thank you for coming today.